All right, so get this. Today we're going to deep dive into atom interferometers,
Oh, wow.
which are like crazy sensitive.
Yeah.
They can pick up like the faintest forces out there in the universe, right?
They can.
And they might even be the key to finally figuring out
Yeah.
this whole dark matter thing.
For sure.
So I was, doing a little research before this,
Yeah.
and there's all this buzz about some
Yeah.
breakthrough, some new kind of atom interferometer that's
Right.
supposed to be way more sensitive than anything we've had before.
Yeah, Northwestern University,
Oh,
some
okay.
researchers over there
Yeah.
developed a new atom interferometer. It's like 50 times
Wow.
more sensitive.
50 times.
Yeah, and it amplifies those faint signals
Oh, wow.
by a factor of 1,000.
1,000.
Yeah.
Okay, now I'm really intrigued. But before we get too deep into that,
Sure.
let's back up a little bit, right?
Yeah.
For those of us who maybe don't have a PhD in physics,
Right.
what exactly is an atom interferometer?
It's kind of like, you know how you have a scale?
Uh-huh.
But imagine if it was super, super sensitive.
Okay.
Like instead of weighing objects, it's actually measuring
Yeah.
the tiniest little forces imaginable, like down at the atomic level.
Wow.
That's essentially what an atom interferometer does.
So are there like tiny little scientists riding on atoms taking measurements?
Well, not quite.
Okay.
But it does involve like some seriously amazing quantum mechanics stuff.
Okay.
It all comes down to this concept of superposition,
Superposition.
which basically means that an atom can exist in multiple states
Oh, right.
at the same time.
Like Schrodinger's cat,
Exactly.
being both alive and dead.
Yeah, it's a pretty mind-bending concept.
Yeah.
But with atoms, what we can do is we can use lasers to split an atom's wave function.
Okay.
So it's almost like we're creating two versions of the atom.
Like atom twins.
Yeah, atom twins, and each of them is traveling
Oh, wow.
along a different path.
So we're sending these atom twins on separate journeys.
Yeah, and you know how real twins,
Yeah.
they're going to have different experiences
Yeah.
that kind of shape them.
Right, right.
Well, these atomic twins,
Yeah.
they encounter different forces along their paths.
Oh, okay.
Then what we do is we bring these two wave functions back together, and it creates this interference pattern.
An interference pattern.
Yeah, it's kind of like, you know, when you throw two stones into a pond
Uh-huh.
and you see those ripples, right?
Yeah.
The pattern of those ripples tells you something about the stones
Oh, okay.
and the forces that acted on them.
So we're basically looking at those ripples to learn about the forces these atom twins experience.
Exactly. And those forces,
Yeah.
they could be anything, right?
Right.
Maybe like a stray photon bumps into one of the atoms.
So even like the smallest things could affect them.
Exactly. And that's where the sensitivity of these interferometers
Right.
becomes really important.
So this team at Northwestern,
Yeah.
how did they get this incredible sensitivity?
They actually use machine learning
Wow, machine learning.
to carefully
Okay.
orchestrate the laser pulses that manipulate the atoms.
So they're using AI to help with a physics experiment?
Yeah.
That's wild.
Yeah. So basically, they use this machine learning algorithm to analyze the interference patterns.
Okay.
And then they can adjust the laser pulses in real time
Oh, okay.
to compensate for like any imperfections or disturbances.
So it's constantly adjusting,
Yeah. Yeah.
like a self-correcting system.
Exactly. And this lets them use like hundreds of laser pulses to amplify the signal
Wow.
without introducing any errors.
Okay, so it's like having this like super steady hand guiding the atoms.
Yeah, exactly.
Even though there's all this chaos going on around them.
It's kind of like that, yeah.
Okay, I think I'm starting to understand why this is such a big deal, but let's get down to brass tacks.
Sure.
Why do we care about measuring these tiny forces in the first place?
So remember the biggest mysteries in physics is dark matter, right?
Right.
Makes up like 85% of the matter in the universe.
85%, yeah.
But we've never been able to actually observe it directly.
It's like invisible, right?
Yeah, totally invisible. We only know it's there because of its gravitational effects.
Yeah.
Like on galaxies and galaxy clusters.
Right, like this like invisible scaffolding
Yes, exactly.
holding the universe together.
That's a great way to put it. And this is where atom interferometers come in.
Okay.
They're so sensitive, right?
Yeah.
That they can potentially detect these really faint interactions
Okay.
between dark matter particles and like normal matter.
So instead of just, guessing that dark matter is out there,
Right.
we might actually be able to like detect it.
Exactly. We'd be able to see it directly.
Okay, so this is starting to sound pretty groundbreaking.
It is.
But it goes beyond dark matter too, right?
Oh, yeah, for sure. We can also use atom interferometers to detect gravitational waves.
Gravitational wave?
Yeah, you know those ripples in space-time
Oh, yeah, yeah.
caused by massive objects colliding.
Like black holes.
Exactly, yeah.
I remember when those were first detected. That was huge.
It was a big deal, for sure.
But the current detectors,
Yeah,
they can only like pick up certain frequencies, right?
exactly. And atom interferometers,
Okay.
they could potentially detect gravitational waves at like much lower frequencies.
Oh, wow.
It's like opening up a whole new window into the universe.
Like we could actually hear the universe.
Yeah,
In
exactly.
a whole new way.
Uh-huh. And those are just two examples.
Yeah.
There's like so many potential applications for this technology.
So we're just scratching the surface.
Absolutely, yeah.
All right, you've definitely piqued my curiosity.
Okay.
So how do we actually use these atom interferometers to detect, dark matter, gravitational waves, all that?
Well, to really understand that, we need to dive a little deeper into the physics
Okay.
behind it all.
My brain is officially in sponge mode. Let's do it.
All right, let's do it.
Okay, so walk me through how we use these atom interferometers to actually detect something like dark matter
Okay.
or gravitational waves.
All right, so let's start with dark matter.
Yeah,
The idea is that dark matter particles, even though we can't see them,
right.
they might interact
Yeah.
very weakly with regular matter.
Okay.
So it's like,
Okay.
imagine like a ghost
Okay.
passing through a wall, right? You don't see the ghost.
Right.
But maybe the wall kind of shivers a little bit.
Okay, so we're looking for those tiny shivers from dark matter.
Yeah, exactly.
These atom interferometers.
Right. So picture this. You've got your atom interferometer running.
Yeah.
Those atom twins are cruising along their paths.
Uh-huh.
And then, boom, a dark matter particle just happens to,
Yeah.
pass through a bump into one of those atoms.
Okay.
And when it does that, it's going to ever so slightly
Okay.
change the atom's momentum.
So it's like a cosmic bang of billiards,
Yeah,
but
exactly.
with invisible balls.
Yeah. Yeah, and that tiny change in momentum,
Yeah.
that little kick,
Yeah.
that's going to show up in the interference pattern.
Okay.
When the atoms are recombined,
Okay.
we're going to see a slight shift
Yeah.
compared to what we would expect if there was no interaction.
So it's not that the atom interferometer is like seeing dark matter directly.
Right.
But it's picking up on the consequences of it being there.
Yeah, exactly.
Oh.
So that's why this new level of sensitivity is so exciting, right?
Right.
It allows us to detect even smaller kicks,
Uh-huh.
which could reveal the presence of dark matter particles that were just like
Okay.
completely undetectable before.
Okay, what about gravitational waves?
Okay.
I know they're like ripples in space-time, but I'm not really sure how those would affect
Right.
atoms in an interferometer.
Yeah, so think of it this way.
Okay.
You got a gravitational wave
Yeah.
passing through the interferometer.
Yeah. Uh-huh.
And it's stretching and squeezing
Okay.
the very fabric of space itself.
Wow.
Even if it's just by a tiny amount, right?
Okay.
That means the distances that those atom waves travel
Yeah.
along their paths,
Uh-huh.
those are going to change slightly.
So the interferometer itself
Yeah.
is getting like whooped
Kind of.
by the gravitational wave.
Yeah. And those distortions,
Okay.
however small,
Yeah.
they're going to show up
Okay.
in the interference pattern.
Okay.
You might see the fringes of the pattern
Yeah.
kind of shift
Yeah.
as the gravitational wave passes through.
We're using these tiny atoms to pick up on ripples in space-time.
I know.
That's crazy. So what kind of gravitational waves could we detect with this new, more sensitive interferometer?
So one really exciting possibility is detecting gravitational waves from the very early universe.
Wow.
Like just moments after the Big Bang,
Okay.
these primordial waves, they'd be incredibly faint by the time they reach us.
Right.
But a sensitive enough atom interferometer
Yeah.
just might be able to pick them up.
It's like a cosmic echo from the beginning of time.
Pretty much, yeah.
That's wild. And that's just one example, right?
Oh, yeah, for sure.
We could use this tech to detect gravitational waves from
Yeah.
sources we haven't even imagined yet,
Right.
potentially revealing all sorts of new phenomena in the universe.
Exactly, yeah.
Okay, this is all incredibly exciting, but I imagine there's got to be some serious challenges involved in actually building and operating these atom interferometers.
Oh, absolutely.
Remember how you said even a stray photon
Yeah.
could mess up the measurements?
Exactly.
So building an interferometer that's sensitive enough to detect dark matter or those faint gravitational waves,
Yeah.
that must be a massive engineering feat.
It is. It's a huge challenge.
So what are researchers doing to overcome those challenges?
Well, they're developing new designs for atom interferometers that are larger and more robust.
Okay.
So they're less susceptible
Uh-huh.
to external vibrations and noise.
Okay.
And they're also using really cutting-edge data analysis techniques,
Oh, okay.
including,
Like a-
machine learning,
Right.
to sift through the data and pick out those really faint signals.
It's like trying to hear a tiny whisper in a hurricane.
Yeah, it's a great analogy.
But we have these incredibly powerful tools.
Yeah, it's amazing how different fields from physics to computer science are coming together to
Right.
really push this research forward.
So what's the ultimate goal here? What are researchers hoping to achieve with these atom interferometers? Big picture.
So for many, the holy grail is the direct detection
Yeah.
of dark matter particles.
Okay.
Imagine, like, not just knowing dark matter's out there,
Right.
but actually identifying what it's made of,
Wow.
studying its properties.
Okay.
That would completely revolutionize our understanding of the universe.
Yeah, that would be a game changer.
It would, yeah.
What about gravitational waves? What new insights could we gain from detecting waves from the early universe or other unexplored sources?
So one of the big questions is whether Einstein's theory of general relativity,
Okay.
Our current understanding of gravity
Right.
holds true
Yeah.
at those extreme scales.
Okay.
And detecting gravitational waves from different sources at different frequencies, that could help us
Yeah.
test general relativity
Okay.
in ways we never have before.
So we could potentially uncover new physics
Yeah.
beyond what even Einstein envisioned.
Exactly. And that's the beauty of scientific exploration, right?
Yeah.
We never know what we're going to find
Right.
when we delve deeper into the unknown.
I have a feeling this is just the tip of the iceberg for atom interferometry.
Yeah.
What other possibilities are out there?
Well, some researchers believe that atom interferometers, they could be used to create incredibly precise
Okay.
navigation systems.
Wow.
Far more accurate than GPS.
Okay.
Imagine like self-driving cars
Yeah.
that can navigate with pinpoint precision,
Okay.
even in areas with like poor satellite reception.
That's incredible. So it's not just, physics and astronomy.
Right.
There are all sorts of applications.
Oh, yeah,
Put
absolutely.
this technology.
And atom interferometers could also be used to study
Yeah.
Earth's gravitational field in more detail than ever before,
Oh, wow.
which could lead to new discoveries about our planet's
Okay.
interior structure and dynamics.
We started with mind-bending physics and ended up with self-driving cars.
I know, right?
And a deeper understanding of our planet.
Yeah.
It's amazing to see how these tiny atoms
Yeah.
can unlock such huge possibilities.
It really is, and we've only just begun
Yeah.
to explore
Right.
the potential
Yeah.
of this amazing technology.
So it's wild to think about all these applications, right? Dark matter, gravitational waves, self-driving cars. What else is out there?
I mean, there's a lot of potential avenues that researchers are looking into.
Yeah.
Like, for example, some people think that atom interferometers could actually help us understand dark energy.
Dark energy.
Yeah.
That's like the thing that's causing the universe to expand faster and faster.
Exactly. So, instead
Yeah.
of just measuring the effects of dark energy,
Wow.
we might be able to, probe its nature
Okay.
directly.
Wow.
It might be possible
Yeah.
to use atom interferometers to detect subtle variations
Okay.
in the strength of dark energy
Uh-huh.
over time
Yeah.
or space.
Okay.
And that could give us clues about,
Yeah.
where it came from, its properties.
We're talking about rewriting our understanding of the universe here.
Pretty much, yeah.
And beyond just, exploring these big mysteries,
Yeah.
it sounds like atom interferometers could also revolutionize
Right.
more practical fields too, right?
It could.
What kinds of things?
So imagine using them to create ultra-sensitive sensors
Okay.
for things like medical imaging or
Oh, wow.
environmental monitoring.
So from the cosmos to the human body, it sounds like atom interferometers.
I know. It's crazy.
To have a huge impact.
Yeah, and honestly, I think we're just scratching the surface of what's possible.
It really is amazing.
Yeah.
We started with mind-bending physics, and now we're talking about
I know.
Self-driving cars and understanding our planet better.
It's incredible how these tiny atoms
Yeah.
can lead to such big possibilities.
It really is. You know what? This whole deep dive has been incredible.
It has.
I had a vague idea of what atom interferometers were before we started.
Yeah.
But now I'm seeing how they could fundamentally change how we understand everything.
Right.
From the tiniest particles to the largest structures in the universe.
It is remarkable, isn't it?
It is.
I mean, you're manipulating atoms at the quantum level,
Yeah.
and it leads to such profound insights.
And the fact that we're combining these super precise experiments
Yeah,
with cutting edge tech like machine learning,
I know, right?
that just blows my mind.
It really is a testament to
Yeah.
human ingenuity
Sure.
and the power of scientific collaboration.
Yeah.
You bring together different disciplines, you push the boundaries of what's possible,
Right.
and we open up all these new realms of exploration.
Well, on that note, I think we've reached the end of our deep dive into the amazing world of atom interferometers.
It's been quite a journey.
It has.
I hope our listener is feeling as inspired as we are by the potential of this technology, who knows what incredible discoveries await us in the years to come.
Yeah, and for anyone who wants to keep exploring this topic, there's tons of information online in research journals.
Oh, for sure.
Don't be afraid to dive in and learn more about this amazing field.
Yeah, keep that curiosity alive and never stop exploring the wonders of science in the universe.
That's great advice. Until next time, keep looking up at the stars and keep wondering about the mysteries they hold.